So hi everyone, welcome to the second video of the class Combinatorics 2 at Stockholm University. And so today here's the title, Functions and the Pigeonhole Principle. And so this is a short summary of these sections in the book. And so the book starts out by talking a lot about the following, like about sets, products of sets, subsets, what's a function, what's a relation, so these are all things very important, and so this is all good to know. However, for this class, we're really interested in very concrete things, very like counting functions, how many there are. And so this is like essentially belongs to a different class, but still, read about it, especially if you feel a little bit unsure about this. So for us, so the picture is the following. So we have a set A. This is the domain of our function. This is where the function starts out. Then we have a function f. And maybe write a little bit down here to a set B. Now this is called the codomain. Codomain. And so what it does is simply it takes an element in here, like little a, and it maps it to a unique point in B. Okay, and then, well, what is also important about this, so it's a very simple, very powerful general concept. Well, there's one important thing, namely if you look at all the, and for any element you could look at all the images, the elements where it maps to, then so this image is called the range. Okay, so the range is just a set of all the image elements that come from an element in A. Okay, so this is something I hope you've seen before. Now for us, we're talking about finite sets. So whenever you talk about finite sets, that's where combinatoric really plays the big role. That's what combinatoric does. So here, both of the number of elements, this is what this means, the number of elements should be finite, and so in the book we call it n, and this is called m. Now m and n, if you say it, is a little bit hard to distinguish, and so I actually call, instead of m, for me this is r. Okay, so this is r, so the number of elements. So we started having like r elements, and each element gets mapped to an element in the set with n elements. Okay, so let's start. We want to count things, so we want to count functions. So we want to count this first little observation. So prop stands for proposition. It's like an observation, like a property. So we want to count, so this means the number of functions from A to B. How many functions are there from A to B? Well, for each element in A, we choose among n elements in B. Is order important? Well, yeah, definitely order is important. And we can choose with repetition. And so all these objects are distinct, they're labeled, they're numbered. So this is just like counting arrangements, it's something we've seen before. So we already know what the formula is. So we have first we have like n choices, or a second we have n choices, and so forth. In total we have r choices. do this r times, so we have n to the r. Okay, so remember the small table we've seen last time, that's something we already know. Okay, so this was so very easy, so a good start here. So let's talk about, let's make this a little more interesting. So there are certain functions which are very important. So these functions are called injective and surjective. So let's first talk about injective functions. Okay, so here's the definition. An injective function, so a function is injective if whenever you take two elements in A which are distinct, so different, they map to different elements in B. So it can never happen that you have two things which are different and somehow will go to the same element. That's not allowed. So here's a little observation. So if F is injective, I claim we can already say something about R and N. What can we say about this? Well, we have R elements in A. If we now look at what happens if we map this to B, well, all these elements will still be different. So we have R elements in B, which means that N has to be bigger than R, so it has to be at least as big as R. So N has to be at least as big as R. So if R would be bigger than N, then we would know that there cannot be any injective functions. So the count would be 0. And so here's now the proposition. How many injective functions are there? Well, think about it. Again, it's very easy. We have like n possibilities for the first element in A. Now for the second element, we cannot choose the one we mapped before already, so we only have n minus 1 choices among the elements in B, and so forth. Less and less and less. So in total we get like, we do this R times well, what is this? N factorial over n minus r factorial. And so this is not surprising because, well, we choose R times among n elements where the order is important, but we do not allow repetition. So this is counting permutations, and therefore this answer, we already knew this before. You might want to cut this out. This is really not good. Okay, well, we finished this. I have to say something about this. Okay, so there's another class of functions which is very important called surjective. So let me write down the definition again. If the range of F is equal to B, then it's surjective. What does it mean? It means that every element in the codomain, every element you pick there, there will be an element in A which maps to this element. So the image, really, everything you map to is all of the codomain. So this is surjective. And again, let's make a little observation. If F is surjective, can we say something about R and n. So R was the number of elements in A and the number of elements in B. Is there any kind of relation if it's surjective? Well, I claim that in this case R has to be at least n. So why is that? Well, think about the n elements in B, pick one of them, there will be an element in A. You can do that for every element in B, there will be an element in A mapping to it. Of course, this has to be different, because, well, it should map to different guys. So we get, in total, we will get n many elements in A, so the number of elements in A has to be at least as big as n. So now counting. Interesting thing here is now counting the number of surjective functions. And strangely enough, so like, you think about it, the definition of surjective is even easier than injective, and the counting injective function was easy, but now counting surjective function is not that obvious at all. So here's the theorem. Let me just write this down. And I really hope I made no mistake, because if you look at this, this is quite a mouthful. So, so this is a formula which you might say, wow, how am I going to remember this? So you will be able to remember this, and maybe, so first of all, we look at an example, but also later on, so we won't prove this now, we'll prove it later, we'll prove it, I think, next time. And once you see the proof, once you have an idea of why it looks so strange and so weird, then will also be easier for you to remember this. Okay, so now at this point, let's just do an example. And maybe I do it here. Okay, so here's the problem. We have like 4 distinct balls. So remember, distinct means labeled, it means numerated. So we have 4 distinct balls, and you want to put them in 3 also distinct labeled boxes. And what's the outcome of doing this? Well, now there's a little twist here, is that every box should be used. So there should be no box which is left empty. So how do we do that? Well, it should be no surprise. Well, if you think about it, we have our 4 distinct balls going into 3 distinct boxes. This is just like a function, counting functions. From a set with 3 elements. No, I'm sorry. 4 distinct balls with 4 elements and 3 boxes. And we're counting all these functions, and this thing that no box should be empty means that every box is used, so every element in the codomain is used, so it's surjective. So we're counting surjective functions with these parameters, and so we know what the answer is. We have to just use this formula. Now this formula looks complicated, so therefore let's do this very slowly. So if you plug in k equals 0, well, minus 1 to the 0 is just plus. We can forget about that. So now we have n, which was 3. So 3 over 3 minus 0, which is 3, times n minus k, so 3 minus 0, which is 3, to the r, to the 4. Now k equals 1. K equals 1 is minus 1 to 1, so it's a minus. This is called alternating. So we have a minus here. Now we have again 3. 3 minus 1, which is 2, times 3 minus 1, which is 2, to the 4. Now, alternating these, so we now have minus 1 to the 2. So we do a plus 3 over 3 minus 2, which is 1, times 3 minus 2. You see all is here the same numbers. 3 minus 2, which is 1, to the 4. And then again a minus, because now k is, well, 3. And so with minus 1 to the 3, 3 over 3 minus 3, which is 0. And 0 to the 4. So the notice is that here we get a 0. We can forget about this. And this will always be the case. So once you go up all the way up until n, you will have always a 0 here. And if r is usually always positive, we get a 0. So this will be 3 terms here. And of course, you can just compute it. You should do that. You should get 36. OK, so now, so this is like the one big thing in this section is talk about surjective functions. Now we will make a little twist here. There is one more important topic coming here. And to understand that, we will change this problem. And namely, what we will do is we will change distinct boxes to identical. So maybe you forgot about to put the labels on your boxes, and you have all the boxes look the same. And now you say, oh my, now how do I do this? How do I count now how many ways I can do this? And so, of course, the answer won't be the same. Well, I won't erase this immediately. Namely, instead, let's think about this. If you have these boxes, so remember, okay, so let's show a picture. So we have 3 boxes, like, we get these 3 boxes here. And now we cannot distinguish them. So maybe like we have these 4 distinct, so labeled balls from 1 up to 4. So maybe the first ball is here, the third ball is here, the second ball is here, the fourth ball is here. But now, someone comes in, like the dog plays with the boxes, and suddenly they look different. Maybe now that one's here. The first one and the third one is here, and the second one is there. And so, in the previous setting, if these are distinct boxes, it would make a difference. We would count them twice. We count this one and we would count that one. But now, because they're identical boxes, if you come in, you cannot distinguish them. For us, it's now the same outcome. Right? We have like 1 3s in one box, 2s in one box, and 4s in one box. That's it. And so think about it. Of course, you can come up with lots more examples. So all what you have to do is you have to just permute them. So if you would permute all of them, so how many ways can we permute them? Well, we have 3 boxes. We can permute them in 3 factorial ways. So that means among all of these 36 examples, 36 outcomes we had before when the boxes were distinct. Now, when the boxes are identical, what we do is we have all these essentially 3 factorials, so 6 different kind of outcomes we had before, and they give you now all the same answer. So we divide by it. And so the answer will be 6. Or maybe you want to write down all these answers. So let me now write down like the general, the general setting, the general definition here. Okay, so here's the general definition. So when you want to count the number of outcomes of putting r distinct balls in n identical boxes, now this is the main point here, such that no box is empty, then what do we do? Well, just as before here, we count the number of surjective functions given by this crazy formula, and then we divide it by n factorial. And so this number is called the Stirling number of the second kind. And it's abbreviated in this way. And so if you meditated a little bit about this, what's really interesting here is that we now know that this is actually a number. It's a natural number. It's like, it's like 1, 2, 3 or 0 or whatever, but it's a natural number. This is not at all obvious, right? Why should n factorial divide this thing? So this, but now we get this just simply from this observation that this equals, well, observation is good, but this equals this number. And so another way to think about it, and this is often also like something you should remember it in this way, if I would ask you what is the number of surjective functions from a set of R elements into a set of N elements, what is it? Well, it's this number here, but just bring it on the other side. You should think about the answer should be it's n factorial times S of R comma n. Now there's an alternative way of thinking about Stirling numbers. Let me write this down here. Okay, so the Stirling number of the second kind SR, and you could also think about it as a number of partitions of a set of R elements, 1 up to R, into n non-empty subsets. So let's just look at our example again, where R was 4 and n was equal to 3. And so here in this case, well, we have like 4 elements. 1, 2, 3, and 4. And so now we want to put these balls in the boxes. And so for instance, like over there, let's look at the first example. 1 and 3 was in the same box. 2 was in one box. And 4 was in one box. But also maybe, that's what just like to illustrate that in this way, it would give you the same answer. And so, of course, in this way, like 4 would be in one box, 1, 3 would be in one box, and 2 would be in one box. So this is just the way to think about it. We have these 4 balls, and now we just subdivide everything. So maybe like, in this case, we choose these 1, 3 in one subset, and this in one subset, and this in one subset. And this is called a partition of the set. And many, as a disjoint union of subsets, and none of them should be empty because, in these n non-empty subsets, it should be all non-empty because, well, we have these n boxes and none of them should be empty. So there should always be something in there. And so I hope this is a kind of a nice way of thinking about Stirling numbers. And there are some examples in the book which use this. OK, so now let's turn to the very last topic of this session. This is about the pigeonhole principle. Okay, so what is the pigeonhole principle? Well, it has many different names in different languages. So the idea is that, just use our box and balls example again. So we have these 3 boxes and we have like 4 balls. And you want to put them in the boxes. Can you do that so that in each box there's at most 1 ball? Well, you try here. Now we cannot put the second one in here, maybe there, maybe there. But now the 4th ball has to go somewhere in there, maybe here. So no, it's not possible. And that is the pigeonhole principle. So it's a very, very, very simple principle, but it's very powerful because it's so general. So in math terms, we can formulate it in the following way. R is bigger than n, so we use the same notation we had before, then diagram F is not injective. So why is this the Pigeonhole principle? Well, so in this case R was 4, and n was 3, and I claimed there was no way of assigning to each ball a box, so that the function becomes injective, so that different balls go to different boxes. No, there have to be at least 2 balls which go to the same box. So this is the Pigeonhole principle, and we already proved it. Somewhere above, what we've seen is like that if F is injective, then n has to be at least as big as R. So that's precisely the same statement, but just in a different direction. Like, just reversing it. Okay, so think about this. Well, like there are many, many examples of for the Pigeonhole principle. The classical one is like if you have a room of people, at least 13 people, and there will be at least 2 of them whose birthday will be in the same month. Right? So in this case we have 13, and we have, what are the boxes? The boxes, so the pigeonholes, these are the months. So 12 pigeonholes, but 13 pigeons, so at least 2 have to go to the same pigeonhole. So I will make it short. I will just mention one example in the book. This is you choose 6 numbers out of 1 up to 9. I claim then 2 of them sum up to 10. So that's the statement. So you pick 6 numbers, any kind of numbers, and there will be at least 2 of them which sum up to 10. So we have to find the pigeonholes. And often the best way to think about this or to come up with an idea is to really, like here, consecutively choose some numbers. So, and maybe you choose like 1. Okay, so maybe the second one you choose is 2. And maybe 3. And maybe 4. And maybe 5. Now we have one more, 6. But 6 plus 4 is 10. And so that gives us the idea that maybe, these really come up in pairs. So 4 belongs to 6. 3 belongs to 7. 2 belongs to 8. 1 belongs to 9. What about 5? Well, 5 belongs to itself. So essentially, if you want 5, 5. And so these are our pigeonholes. So whenever you now choose a number, it will fit into one of these pigeonholes. So another number, and another number, and another number. After you did like 6 of these choices, the 6th one has to be in one of the pigeonholes you already had before. So in that case, like before, these numbers will sum up to 10. Okay, and that's it for today. So, well, I want you to I should write down some examples again. You should have a look at. And so here they are. So here are the problems, so the examples I want you to have a look at. So this is really the best way to learn all this. Okay, so see you next week.